Let's look at right circular cone. So we need 2 points, A1, B1, C1, and let's say that the vertex of the cone is at the origin. So 0, 0. Okay, and we require another point on the axis of the cone. So let us say A2, B2, C2, and let's say this is on the Z axis 0, 0, and let us say this is 5, right? So this is the axis and this point is on the axis. The vertex is at the origin. Now we require one more variable. Let us say A. Okay, now let's define the formula for generating the right circular cone. A square, no, A2 square plus B2 square plus C2 square, and then x minus A1 square plus y minus B1 square plus z minus C1 square, and then cos square A is equal to x minus A1 times A2 plus y minus B1 times B2 plus z minus, no, this should be inside the bracket, B2 plus z minus C1 times C2. Yes, and this whole thing should be square. Okay, so we got the cone. Actually, what we got is a double cone, right? So let's focus only on the top part. Now here, this z axis is the axis of the cone. Now we want a point on the cone, on the surface of the cone. So let's use GeoGebra's function, point in EQ1. So by default it is taking it as 0, 0, 0 because that is also a point on the cone. But we don't want, we want some other place. So now irrespective of how I move it, it looks as if it is inside. No, it is on the surface. So let's say I put it here. If I rotate it, it is on the surface, right? So this point will always be on the surface. Okay, now let's define two vectors using these 2 points. So use u is equal to, let's say u is equal to vector a comma c, right? Similarly vector, and now what I'll do is I'll say I need a point, so 0 comma 0 comma z of c, right? Z of c. So it looks as if this is smaller than this, but they are at the same level as far as the z axis is concerned. Okay, now here this vector v is part of the axis. This vector which connects the origin to the point C, and if we take it beyond, then it becomes a line. So this line is called the slant line, axis vertex. Now we want an angle. So angle between u comma v. Now see here, it is 57.3, right? Now as I move this, it doesn't matter where I move it, that angle will remain the same. Actually, that is the this line is called the generator of the cone, because you basically decide what angle, then take a line and rotate it, maintaining the angle constant. What you end up with is a cone. Okay, now let's say we also want the this distance from the tip of this vector to this vector. So that's pretty straightforward. U minus v. So actually we get that, right? So if we move it a little bit so that it is exactly on the axis, it becomes easier to visualize. Okay, so angle is 57.3. Now we also want the distance from C to the axis. So what do? We look at the magnitudes. So magnitude of W, magnitude of U, magnitude of V. Let's verify this distance using Pythagoras theorem. So square root of C square minus V square, 7.3, and magnitude of W is 7.3. So that is right circular cone. And by the way, this what we evaluated, 7.3 magnitude of W, is the radius of this cone at this point, right? Because as we go down, radius will decrease. As we go up, radius will increase. So at this point, this is the radius. Now, having done all this, remember, I started off with some specific values. We said the vertex will be at the origin, and the z-axis would be the axis of the cone. If we change it, then some of our calculations goes for a toss. So we need to be careful about that. See, now axis is no more the z-axis. It has to be somewhere here. Okay, just get a feel of this, how you can play around with this. If we change the a value, then the angle, a is nothing but the angle, then the cone becomes smaller or bigger. So remember, this calculations that we saw make sense only when we are talking of right circular cone. So we have to go back to when the vertex was at the origin. That's it. Bye for